Well, good afternoon, everyone. My name is Jerry Zimmerman, and it is my distinct pleasure to be able to introduce this year's SCCM Lifetime Achievement Award winner, Dr. John Marshall. As you learned yesterday, Dr. Marshall is a professor of surgery at the University of Toronto. He is a critical care physician at St. Michael's Hospital, a senior investigator at the Keenan Research Centre for Biomedical Science, and he holds the Unity Health Chair in Trauma Research. His academic interests lie in sepsis and the host innate immune response to trauma and infection. He leads the Canadian Institute of Health funded research programs in novel clinical trial designs and treatment of post-resuscitation fluid overload among critically ill patients. And he has been an active investigator in multiple ongoing clinical trials. He is particularly interested also as a side interest in astronomy and chemistry. These were passions of John in his early life, but that changed as he entered his teens and shifted his focus to the arts. He dropped out of the university to become a filmmaker and spent several years in the commercial film industry editing documentaries, television commercials, before realizing that the path forward was probably improbable. The death of a cinematic colleague at work one day convinced him that staying on this path was the route to an early death, and so he decided to switch his focus. Fortunate for all of us. Dr. Marshall explains he simply changed media, transitioning from mechanically editing celluloid to medically editing the human body. After finishing medical school, he worked for a while developing and teaching an educational program on occupational health and safety. Torn between a career in public health and acute medicine, he entered a surgical residency in Halifax, and it was there that he encountered an article on multiple organ failure authored by the American surgeon Don Fry. It brought together the unsolved frontiers of acute care with a transformational model of infection that infection can mediate, even when critical care practitioners can stave off its immediate consequences. And this set him on a path that led him to a career that included critical care trauma and the associated research on sepsis and the host response to infections. So, ladies and gentlemen, please join me in welcoming Dr. John Marshall as he presents his lecture, Whose Achievement? The Power of Scientific Collaboration.
Well, thank you very much, Dr. Zimmerman, for that very kind introduction, which is in part a précis, I think, of some of the comments I'm going to make today. I wanted to thank the SCCM as well for this honor. I think there is no greater accolade that someone can have than the respect and recognition of one's peers. I want to thank all of you for coming out to the talk this afternoon, and particularly for many old and very, very dear friends and colleagues in the field of critical care. And I want to particularly thank my wife, Mary Morrison, who's traveled all the way from Toronto to San Francisco to be here this afternoon. Thank you, Mary. These are my disclosures for the talk this afternoon, both academic and financial disclosures. I also want to acknowledge that the talk I'm going to be giving this afternoon is being delivered on the ancient and unceded lands of the Ramaytush Ohlone Nation, and that our continent that we live on today has a much deeper and richer history associated with it. I've put forward some learning objectives for the talk this afternoon, but there really is a more fundamental theme, I think, that's going to underline my comments to you today. As I've been thinking about this event over the last 6 months or more, it came increasingly clear to me that there will be a number of you sitting in the audience wondering, who the heck is this guy? And what has he really done to deserve an award such as this? It's a really good question, And as I thought more and more about it, I realized the answer is not very much at all. And that really frames the comments that I want to make today, because I think achievement is not an individual phenomenon, it is a collective phenomenon. And I really want to speak about the role that collaboration plays in achievement in a specialty such as critical care. Now, we live in an extraordinary sliver in the history of this planet. The planet's been here for more than 5 billion years, but the last 200 years have seen change take place at an absolutely unprecedented speed. We've gained tenfold population increase over the last 2 centuries, most of that within the last century and even within the last 50 years, certainly within my lifetime. You can see from this graph how the population has increased. We have made extraordinary advances in technology. The iPhone and mobile phones, and I suspect this is a device that probably more than half the audience today will use sometime in the next 45 minutes, either out of interest or out of boredom, but many other things. The Large Hadron Collider that has allowed us to see the smallest particles in physics, the Human Genome Project, and I'll be speaking a bit more about this, the James Webb Telescope, which has allowed us to see far back in the universe and almost back to the origins of the universe itself. But we've also, as a result of these changes, brought on the world some unprecedented challenges, terrors, and almost existential fears for our future. Certainly the climate crisis is one of these. Migration, overpopulation, and how we deal with the consequences of that. The threat of war, which is no longer the risk of being bayoneted or hit by a blunderbuss, but is having an entire city decimated by a nuclear weapon. And then most recently, the emergence of novel pathogens such as the SARS-CoV-2 virus, which went very quickly from a food market in Wuhan, China, to completely change our lives over the last 3 years. This is the framework that I wanted to create for this talk, and I want to start with this quote from the British philosopher Bertrand Russell. In his autobiography, he talks about how 3 passions, simple but overwhelmingly strong, have governed his life: a longing for love, the search for knowledge, and an unbearable pity for the suffering of mankind. I think these aspirations, in one form or the other, shape all of our lives, and I want to give you my particular take on them as they have influenced my life in academic medicine. We are born curious. From the youngest child, one of the first things we learn to do is ask the question, why? And for me, that curiosity took the form of an interest in astronomy, those extraordinary things that existed in the night sky, galaxies, planets, shapes that ancient peoples had imagined as being mythical creatures and animals. And as we've advanced with the James Webb Telescope, this has only become more wonderful, more awesome. The image on the right of that slide, the little red dot in the center, is a galaxy that's located 13.5 billion light years away from us. Now, the Big Bang occurred 13.8 billion years ago, so we are seeing almost to the very origin of the universe itself. And the thing that's astonishing is how rich and how full of light it is. I changed my focus, or certainly vacillated between science and the arts when I was younger. I studied theater with a woman by the name of Dora Moore, who was one of the pioneers of Canadian theater. She founded the Stratford Festival. And she was also a huge force in my life, my very first mentor, really. She humored my teenage attempts to play Ferdinand in The Tempest. But one day took me aside and said, John, you should really go into medicine. You could do research. So, of course, I didn't take her at her word at the time. I thought, oh, you foolish old lady. But she said something, what she had told me really had changed my life. I decided that what I wanted to do was to become Canada's answer to the Swedish director, Ingmar Bergman. And so I became a filmmaker. I dropped out of university in my second year of an arts course and went to work in the commercial film industry. I spent 2 years there learning the craft of editing bits of celluloid together and bits of magnetic tape to be able to tell the story. But what I realized is the stories I was telling were pretty banal, pretty arid, and really not focused on anything other than trying to sell instant mashed potatoes or cigarettes. So for a variety of reasons, I decided this is not where I want to be as I aged. I took Mrs. Moore's words to heart and enrolled in medical school. And as Jerry said, I like to think of this as really simply being a recognition that there are much more satisfying media to work in than editing celluloid. And ultimately, I became a surgeon. Anybody in this room who's been through medical school understands the terror and the awe that one experiences as a medical student. One's confronted with a vast amount of facts that seems to be limitless, and spends an enormous amount of time trying to learn minutiae of anatomy, of physiology, of histology. And behind all of that attempt to learn is this terror that if I don't know the insertion of the pectineus muscle, or if I don't know the clinical features of MEN type 2 syndrome, some patient who has placed their trust in me is going to suffer as a result of my ignorance. What one learns as one moves on in medicine is that we don't really know very much about anything at all, and that what we do and what we provide our patients is partly coming from knowledge and the application of that knowledge, but much more coming from a sense of compassion, a willingness to listen to them, and a willingness to be with them in a time of need. In fact, this is where the word hospital comes from. It's not a coincidence that the words hospital and hospice share the same Latin root. It is the Latin word hospes, which means a stranger or a guest. So this is a photograph of a hospital in 1918 at the time of the influenza pandemic, where all that could be done for patients who were suffering from influenza was to cohort them, to provide them some comfort, and to allow them to either get better on their own or to die of their disease. Now, this changed fundamentally 70 years ago, the time of a polio outbreak in Copenhagen in Denmark. The Danish anesthetist Bjørn Ibsen came up with the very simple, ingenious, and almost self-evident idea that if a child with polio who was not able to breathe on their own couldn't breathe, perhaps we could support them by doing a tracheostomy and by manually bagging and ventilating them. And so what he did is he tracheostomized a number of young children, recruited a large cadre of medical students and residents and other trainees to sit with these children 24 hours a day to provide them with bag ventilation through the tracheostomy. It seems perhaps tough work for the residents, but it was transformational because the mortality with respiratory polio in Copenhagen fell from 90% to 25% as a result of that advance. Now, the ICU, though, has had other consequences, some intentional and most inadvertent. The ICU created a whole new spectrum of diseases. These were the diseases that arose in patients who, in the natural course of things, would have passed away, but who are kept alive on exogenous support and therefore develop conditions that never existed in the natural world before: sepsis, acute respiratory distress syndrome, or the multiple organ dysfunction syndrome. And in many ways, the diseases we treat in the ICU are entirely iatrogenic. They occur because we've been able to avert death through ICU support, but that ICU support becomes a critical element in their subsequent evolution. This is where I became involved in intensive care. I had started my surgical residency in Halifax, Nova Scotia, Canada, and in the wisdom of the program committee, having just moved to a strange city and not knowing anybody, they assigned me to a rotation in anatomy. And I was asked to perform dissections to identify the course of the fifth cranial nerve. Now, that was relatively limited in its excitement, and so I, in fact, spent most of my time in the library of the university there, thumbing through surgical journals and trying to get a sense of what this specialty that I'd committed myself to actually entailed. And so it was at that time, as Dr. Zimmerman mentioned, that I came across this particular paper by Don Fry, a friend and colleague from Louisville, Kentucky, and more recently from Chicago, who had written a paper on what he called multiple system organ failure. The recognition that when very sick patients become ill, they develop many different aspects of dysfunctional organs. But what Don did in this paper was he put these together into a model and showed that there were common causes and common prognoses to that process of multiple organ failure. And this was really a revelation for me because it framed a problem which in many ways had simply been characterized as this is really complicated into a disease or a syndrome that one could begin to imagine had causes and potential loci for intervention to treat it. So when I finished my training, I moved to Montreal, where I worked with Jonathan Meekins, who was the chair of surgery at McGill University. Joe gave me an extraordinary latitude to kind of play with ideas and explore things at the very far edges of what we actually knew or understood, and some things that perhaps strayed a little bit over those edges. But Joe was a marvel of humility. I remember one day doing rounds in the ICU, and we were examining a patient who we thought was infected, but we weren't quite sure what was going on. And Joe turned to me and said, "You know, I really don't know how to diagnose pneumonia." And this was transformational for me. I had up until that point assumed that not being able to diagnose pneumonia was my failing. It was because I did not know enough, and the solution was to read more, to study more, to see more patients with pneumonia, and to correct that deficiency in my knowledge. What Joe was saying to me was that it's not my deficiency, it's our deficiency. We don't know how to diagnose pneumonia. That was a call to figure out how to do it and to undertake research that would allow us to learn that answer. And so I had the opportunity to, both in Montreal and subsequently, indulge in a career of discovery in multiple different areas, looking at the problems of sepsis and critical illness. And I think anybody who has done research will appreciate the image on this slide. This is a young computer scientist named Katie Bowman. She was the person who wrote the algorithms that allowed the first imaging of a black hole. And the expression on her face so beautifully captures that sense of awe, of wonder, of delight, of surprise, and almost of embarrassment at having seen something in the universe in a way that the universe has never been seen before. It's an absolutely intoxicating feeling. So I've had the opportunity to exercise this feeling in multiple different areas, looking at whether or not the GI tract was the undrained abscess of multiple organ failure, or whether patients died because of infection or the response to infection, looking at why the inflammatory response persisted, why neutrophils failed to die when they were genetically programmed to do so, trying to quantify organ dysfunction using a score, trying better to stratify and stage patients through the building of descriptive models of organ dysfunction. And much of this came through being involved in clinical trials in sepsis, which, as you well know, have been a source of continuing disappointments. So individual discovery is fun, but individual discovery doesn't change the world. The world changes through collaboration that is often informed by discovery, but is critically dependent on people working together. This is Peter Higgs, who in 1964 proposed the existence of a particle that has come to be known as the Higgs boson, or the God particle. It gives mass to all elementary particles. But Higgs proposed this in 1964. It wasn't until 2012 that the existence was actually confirmed. And this required a massive international collaboration, a 27-mile circumference circle under the border between France and Sweden, and almost $10 billion spent on building the Large Hadron Collider. Now, we talk a lot in critical care about teamwork, and collaboration and teamwork share many common features, but there are important distinctions, and I think they've led to collaboration being undervalued in what we do. Teamwork is very much focused towards a specific goal or a specific target. It's inward focused on reaching that target. It focuses on the individuals who are going to be doing that, and it strives to build cohesion amongst those individuals. It can create competition, certainly in sports, that teams compete against one another, but they rely on their internal cohesion for success. Collaboration, on the other hand, is outward-looking, often at a much grander scale, and rather than looking to be cohesive, it wants to be accommodating and as inclusive as possible. And the differences are, I think, that teamwork focuses on a specific task. Collaboration focuses on a much larger vision. And so it's through collaboration that one can really accomplish and achieve very large objectives. Collaboration is, humans are unique, I think, amongst living species in our capacity to collaborate at very large scale. Obviously, bees, termites can collaborate to build homes, but we collaborate to build societies. And really, our emergence as modern humans has been a consequence of this capacity to collaborate. Collaboration requires that we develop a common language, that we're speaking about the same things, that we can communicate broadly about them. It requires that we develop means of communication, that we have shared goals, that we come up with common tools, and that we come up with social structures that allow us to work together. So about 5,000 years ago, there was an explosion in collaboration that resulted in the emergence of religions, the emergence of societies that were larger than simple small communities, the emergence of political structures, the emergence of nations. And today, of course, we take collaboration for granted, but it really is the reason that we're able to be here today at this meeting and that we're able to work together in the specialty of critical care medicine. Hospitals are a beautiful example of an institution that functions because of the collaboration of all of its parts. Cities are the same thing. Cities depend on all the different components that make a city run smoothly. And the world itself depends on collaboration, whether it's the ability to forecast weather by collaborating at small scale all around the planet, to enable air travel by coordinating and collaborating in airline schedules, or to communicate through the internet and to be in touch with any place in the world almost instantaneously. But collaboration has another dimension to it, and that is that collaboration doesn't ask for credit. This is a wonderful quote from Ingmar Bergman, the Swedish filmmaker I spoke of earlier, that really resonated with me. Bergman was asked how he wanted to be remembered after he died, and sadly he did die last year. But he spoke about the analogy of the cathedral at Chartres. This was a wooden cathedral that burned down in the year 1020, and after the cathedral was destroyed, the people of the region got together, stonemasons, all kinds of different carpenters, bricklayers, architects, and they built a new cathedral. And it's still standing 1,000 years after that time. No one knows who the people were who built that cathedral. All they know is the cathedral is there and is admired. And that's what Bergman said. He wanted his films to persist as something that was independent of the people that worked on them and that just existed for themselves. Now, in medicine, perhaps the best metaphor for collaboration in medical science comes from the understanding of the structure of DNA, deoxyribonucleic acid. As you know, this is our core genetic material. All life on the planet shares DNA, and it has two fundamental features. DNA defines the sequence of amino acids that make up the proteins that perform the functions of the cell, and it has the capacity to reproduce itself extraordinarily faithfully. The reproduction of DNA is almost perfect. Now, collaboration has taught us a lot about DNA. In the 1930s, it was assumed that the genetic material of the cell was the amino acids, and that DNA was simply a reservoir for phosphates. But the work of people like Avery and MacLeod and McCarty showed that it was actually DNA that was the genetic material. Then in 1952, Watson and Crick defined the biochemical structure of DNA. They won the Nobel Prize in 1962 for this work, and they showed that DNA is a double helix. In doing so, they provided something incredibly important, which was a physical basis for the capacity of DNA to reproduce itself. Watson and Crick are often seen as kind of the founders of our understanding of DNA, but in reality, it's the collaborations that occurred that have allowed us to use that understanding effectively. The large human genome project that completed early in this century and that mapped the entire 3 billion base pairs that make up the DNA molecule allowed us to see what in who we are is written and where in this extraordinary molecule. Just this past year, the Swedish geneticist Pablo Svante won the Nobel Prize for his work in sequencing the DNA of Neanderthals. An amazing accomplishment, and one that shows us as modern humans what we share with these earlier ancestors. And what of them lives on in us. Something like 3% of our genome is Neanderthal DNA. But it's even more profound than that. This is a beautiful study that just appeared in Cell this month. The authors used DNA collected from cadaver samples going back 2,000 years to map patterns of migration into Scandinavia. And what they've been able to detect is migrations that are not recorded in oral or written history. Migrations, for example, from the United Kingdom into Scandinavia. So DNA has actually given us the opportunity to understand at a historical level who we are and where we came from. And then, of course, in the COVID-19 pandemic, DNA is also allowing us to understand why patients get sick. This wonderful work done by the Genomic Consortium, led by intensivist Kenny Bailey in Scotland, has identified some key loci in the genome that confer increased susceptibility to COVID-19 and are therefore targets for therapeutic intervention. DNA is an amazing molecule, and there's a wonderful book that discusses it, this book called Chance and Necessity, written by Jacques Monod, who is a French biochemist and Nobel laureate from the 1960s. Monod pointed out that DNA has two core features. One is this sense of invariance. It is replicated very faithfully from generation to generation, and it's why species persist over time. It's why when you look at a picture of your great-grandfather, you recognize your nose in your great-grandfather, and why there's some constancy in who we are. But the other feature of DNA, which is perhaps as or even more remarkable, is that it is subject to change, very small change, but change that can unfold over a very large time scale. This change happens purely randomly and results in alterations in the proteins that are encoded within that DNA and in their structure. And if those alterations increase the likelihood of reproductive success, they're passed on to subsequent generations. That is the fundamental basis of evolution, and it's the reason that we're here today and why we have the diversity of life that we have on the planet emerging from a primitive biologic cell that existed about 3.8 billion years ago. You can kind of think of reverse engineering of the DNA story as being the mechanism through which we're able to understand the clinical world we live in, through doing clinical trials based on randomization, randomized clinical trials. But what we do is we take the random variability in patients and in countries as the backdrop for our studies. Randomization means that factors both known and unknown will be equally shared across groups of patients. And the constant is that we randomly assign patients to one thing or another. So the only variable that differs between those groups is the intervention, and therefore this is the most potent tool we have for inferring causality. Randomized clinical trials have been kind of the lodestar of our aspirations as scientific clinicians. This slide shows the rapid increase in clinical trials in critical care over the last 40 years. In 1980, there was just a handful being done. In 2020, we're up to almost 2,000 clinical trials being reported each year in PubMed. And it's really important to think about who is doing these clinical trials, because they're not academic institutions, they're not the pharmaceutical industry, they're all of us in this room, clinicians who have some additional skills in investigation and who collaborate together in individual groups. A key, probably the most important part of my academic career has been my involvement with the Canadian Critical Care Clinical Trials Group founded back in 1989. We've done many, many trials on different questions in critical illness. But one of the most important elements of the critical care trials group has been the recognition that to do really impactful and rigorous science, you have to acknowledge and celebrate the social dimensions of science. So we're having our annual winter meeting starting tomorrow in Lake Louise. People will be spending a good part of the day on the ski slopes. They'll be spending the evenings in the bars, having dinners together, dancing in the pub, and recognizing that all of those social interactions are what makes our science so good. This is a model that has substantial traction, and there are now similar investigator-led trials groups, independent from universities, independent from commercial organizations. The ANZIX group has really surpassed the Canadian group in terms of its productivity, but is a real powerhouse. There are the PEDAL Network and the Discovery Network here in the United States, but there are very active trials groups in Saudi Arabia. For example, Yassine Arabi is here, in Brazil, in Ireland, even in North Africa, Southeast Asia, and Latin America. These groups, this is really an expression, I think, of a common desire on the part of clinicians to understand what we do better and to work together better. And they've had an impact. We did this analysis a few years ago where we looked at clinical trials, large clinical trials published in major medical and critical care journals. And we looked at the annual citation rates based on the model of organization of that particular trial. And what that analysis showed, the numbers at the top of each bar are the number of trials in each category. But what that model, that analysis showed was that by a factor of more than 2 to 1, trials coming from formal constituted trials groups are more cited in the literature than trials coming from other particular models. Now, the other thing that has had a profound impact on critical care over the last 20 years has been the scourge of the 21st century, the emergence of a series of viral pandemics. SARS in 2003, H1N1 influenza, Ebola, Zika virus, and then, of course, the COVID-19 pandemic that we have been experiencing over the last 3 years. It has taught us the role that critical care plays in a global public health agenda. These trials groups came together through the International Forum for Acute Care Trialists, published this paper in The Lancet in 2010, where we committed to working together to do cohort studies and clinical trials in response to the H1N1 pandemic. We decided to do clinical trials to evaluate corticosteroids and statins in H1N1 influenza, but discovered that we had only recruited, by the time we had these studies up and running, we had only recruited about 50 or 60 patients before the pandemic had run its course. And so we realized that we had to do better. We had to actually be ready to go for the next pandemic in advance of that pandemic need. So this idea was resonating with others, including with funders who promoted an organization called ISARIC, which is a group of infectious disease researchers and public health researchers. So with them, with INFAC members, with a large number of critical care groups, we worked together to imagine what an appropriate response to a pandemic might look like. And this was first funded in the European Union through what was called the PREPARE platform in 2014. And the clinical trials component of this pandemic preparedness strategy is what became the Revamp Cap trial. So Revamp Cap was imagined as a sleeper trial. It would be a platform trial that could recruit patients to a disease, look at multiple different interventions. It would study community-acquired pneumonia because that's what a pandemic tended to look like. It would be multinational, potentially perpetual. It would have multiple different funders. It would use Bayesian adaptive approaches rather than frequentist approaches, which are just more compatible with a perpetual kind of design. And it would use response adaptive randomization, which means that the trial learns as it goes forward. And if one intervention seems to be performing better than another, more patients get randomized to the intervention that seems to be performing better. So a platform trial, unlike a conventional trial, studies a disease rather than an intervention. In its pandemic iteration, the Revamp Cap trial studied COVID-19, and these were our initial interventions: antibiotics, COVID antivirals, corticosteroids. We very quickly added some immune modulators and anticoagulants as it became apparent that coagulopathy was an important component of this disease. In 2020, January of 2020, we had fewer than 100 patients recruited with CAP, but we rapidly expanded with the onset of the pandemic, so that we have now over 10,100 patients with COVID-19 recruited. We have studied something like 61 different potential interventions. We've had more than 360 sites around the world involved, and we've published 8 different manuscripts looking at the efficacy or the harm of interventions, showing harms associated with the antiviral agents, lopinavir, ritonavir, and hydroxychloroquine, benefit for IL-6 receptor antagonists, divergent results for heparin, contingent on illness severity, and benefit for antiplatelet agents. And as Lisa Higgins showed yesterday, the data for IL-6 receptor antagonists and antiplatelet agents is robust and holds up at 6 months after study randomization. So the platform trial model has gained enormous traction during the COVID-19 pandemic, partly on the basis of Revamp Cap, but perhaps even more on the basis of the recovery trial in England. This is a large platform trial studying COVID-19 in hospitalized patients. It's promoted and supported by the National Health System. It's recruited almost 50,000 patients so far, and it's studied 15 different interventions. All of these have given us information far more rapidly than any other research model in the past has done so. But although I think we can take some pride in the fact that we responded to the COVID-19 pandemic and did derive some answers, I think we also have to be chastened by the fact that there's so much more that we could have done and so much more that we can do. This was an opinion piece from Era Darzi in the BMJ in 2021, where he pointed out that even with the support of the recovery trial, only 10% of hospitalized patients had been studied, but 20% of all ICU admissions. In Canada, we've recruited 2.4% of Canadians who were admitted to an ICU with COVID-19 to the Revamp Cap trial. And although that's now 800 odd patients, it's still not very good. So I think the question is, where do we go from here? And perhaps more precisely, where are we going from here? Because I think that we are at the start of a very important transformational time in the history of medicine. We have seen over time a number of large ideas that have gained a foothold in medical thinking and have really transformed the profession. Back in the early part of the 20th century, the Flexner Report changed medical education in the United States and Canada. It opened the door to residency training programs, to medical schools. It really opened the door to scientific medicine and to teaching hospitals. In the last 40 years or so, through the work of people like Dave Sackett and Gord Guyot and Deborah Cook, the evidence-based medicine movement has taken that on. It has said if the basis of medical practice is science, then we have to assimilate that science and apply that science in practice. And so it's given rise to the Cochrane collaboration, to the technique of meta-analysis, to the development of the many, many guidelines for treating different diseases that we now put so much emphasis in, to bundles and to care paths. And again, it has really been a significant step forward in medical practice. So I think we are on the cusp of a third revolution in the integration of science into healthcare. And perhaps we could call it something like practice-based science. The notion here is that we would embed research into clinical practice. And rather than on rounds saying, I'm not sure what the best thing to do is here and agreeing that we will do this, you would take that uncertainty and randomize patients in the context of a clinical trial. This would be done at large scale, not just within a single hospital, but in platforms that were shared across hospitals, ideally shared across countries, and you would very quickly generate the answer as to whether one approach was better than the other, embedding research in clinical practice. We have the opportunity, I think, in critical care to really be at the forefront of this because of several quirks of our specialty. In critical care, we're not a great place for developing and marketing new drugs. And industry knows this, and really the advances in critical care have not come because pharma has developed expensive new drugs to treat critically ill patients with. It's come because we've learned how to use what we have, but to use it more safely and more effectively. In addition, because the people who are doing this research are not ivory tower academics or scientists associated with drug companies, but rather people who are caring for patients, clinician researchers are actually shaping the critical care evidence-based. I want to just show you this in a little bit more detail. This is an analysis of critical care RCTs published in the New England Journal of Medicine from 1971 to 2022. So this is looking at any trial that either has the word critical or intensive care medicine, sepsis, or ARDS in the keywords. And what you see here is there are 82 trials that have come from investigator-led groups, 10 from industry. So we outnumber industry-funded trials by a factor of 8 to 1. And they come from these same formally constituted investigator-led trials groups. The ANZIX group has published 16 papers, ARDSNet and PEDAL 8, the Canadian Critical Care Trials Group 14. But again, you see groups from all around the world are publishing these trials, and these are groups that are increasingly gaining experience with working collegially and collaboratively with each other. Now, there's an additional reason why the healthcare system might want to support a model such as this. In improving patient care in the ICU and getting patients out of the ICU with fewer complications, we save money. So it's been estimated in Australia that the return is $5.8 for every dollar spent in research. We did a cost analysis with the PROTECT study of DVT prophylaxis that showed the average ICU could save $1 million by switching to low molecular weight heparin. And we also informally looked at the results of the TRICK trial of conservative blood transfusion strategies. Again, significant savings both of scarce blood products and of scarce dollars. So what practice-based science would look like is that we would develop a series of research platforms, initially at small scale and gradually collaborating with each other so they became larger scale. Ideally, these would use a response adaptive randomization to maximize patient benefit from this. We would use embedded data collection, which is now becoming increasingly feasible with electronic health records, and we would work to try to, at least for these data elements, make sure that the data collection systems were internationally compatible. We would seek broad input into the questions from patients, from funders, from policymakers, perhaps like the James Lind Alliance. But that wouldn't preclude individual people doing their own studies, asking their own questions. The more broad the input, the larger the scale of the trial, and the quicker the answers. But this is quite compatible with the model of research we currently have. We would see trial enrollment as a default option, and this has significant implications for thinking about our current approaches to research ethics, which I find, frankly, quite distorted and quite against the best interests of patients. Finally, and perhaps most importantly, we would take the funding of clinical research out of peer-reviewed granting agencies, which kind of give the impression that this is some effete process that is undertaken by academics rather than something that's intrinsic to good healthcare. And it would be, they would be funded out of the healthcare system. So here's a schematic that perhaps shows what this might look like, and I'm indebted to my colleague Patrick Lawler for permission to use this slide. You could imagine, for example, 3 separate platforms, one set up to look at infection, another to look at acute respiratory failure, and another to look at hemodynamic dysfunction. These would all use common data elements so they could share data across the platforms. If you were looking at an issue like the duration of antibiotic therapy, patients might just be recruited from infection. But some of those patients will have respiratory failure, and so those data could be shared across those trials. You could look at a prophylaxis trial where you recruited patients from all 3 different platforms and shared the data together. And then within any platform, you could type the patients. If you were looking, for example, at the efficacy of an anti-endotoxin therapy, you could identify those patients who had endotoxemia in all of those groups and recruit them to that trial. These trials would share data across each other, and they would be organized at as large a scale as possible. So I'm not suggesting that this is simple. There's no question that grand ideas come with substantial challenges in thinking about how one moves forward to actually embedding research into clinical practice. There's a lot of potential obstacles. One of the biggest is academic traditions. We're accustomed to thinking of achievement as being an individual phenomenon measured as the number of first and senior authored publications. And that has to change. There are financial incentives against this because universities use those kinds of metrics to build their foundations and to fund the university. There's a cultural change. We as clinicians are not particularly comfortable about saying, I'm really not sure what I should be doing with this patient. We want something more reassuring to have to treat a patient. But in many ways, there is nothing more reassuring than randomization when you truly do not know the answer. And then, of course, there's challenges of organization and how one actually gets these things to work together. But certainly the experience of the James Webb Telescope, the Large Hadron Collider, the space program, any of these large collaborations shows that these problems can be solved. You know, we have often talked about what we do in critical care as being a matter of trial and error. Where we've tended to put our focus in trying to improve that has been on analyzing the errors. I think we really need to move into an era where we focus on the trials. And I want to just leave you, I think, to me, science is not just about discovery. Science is about equity and building a better world. And I think this has never been put better than it was by the Canadian biochemist John Polanyi, who said that pursuit of discovery is shot through with idealism. Discovery originates in the unsupported belief that the book of creation is open to being read. So I wanted to thank you this afternoon. I particularly wanted to thank a large number of people who played such an important role in my academic and personal life, from mentors to a huge list of colleagues and collaborators. This list was not large enough to put all of the names on it, to a number of students. And then most importantly, to Mary, my wife and partner of the last 45 years, who's tolerated my quirks and my obsessions, my frequent absences, and shares with me my greatest achievement, our greatest achievement, our daughter Kate. Thank you very much.